In Chapter 18, Confidence Intervals for Proportions, we look at a lot of different things that make up this idea of a confidence interval. In class, we talked about the definition itself, about the fact that a confidence interval is centered at whatever our sample statistic is, and it attempts to reach out in both directions, the positive and the negative direction, and hopefully capture the true population parameter. It's very difficult to understand what the heck a confidence interval means without actually playing around with it first and figuring out what happens when we manipulate different aspects. The problem is that when we are creating a confidence interval, there are going to be a few things that we can control and things that we can't. The things that we can't control are the things that are associated directly with the population itself. We're not going to be able to change the population that we're interested in studying. We want to learn about it. That means we have no control over the population distribution. That includes the parameter, which is usually the population mean or proportion. Remember, that is the center of our distribution, or the population standard deviation, how spread out the information is. Where do we expect to see a majority of our data fall? If our data is not normal, we can barely talk about any of these things at all. And this is something that we absolutely can't control. I cannot go out and change my population to make it fit what I want. Now, we can control a few things. The confidence level, which indicates the percent that you're going to be using in your calculations, and the sample size itself, those are the two things that you can manipulate. You can change your sample size, increasing the number of elements within your sample or decreasing it, and changing the confidence level. Remember, the confidence level itself is a balance between certainty and accuracy. You want to make sure that you are correct and that you capture your true population parameter, but you don't want your confidence interval to be so broad that it really has no point anymore. So what we want to figure out is what happens when we change these two things, the confidence level itself and the sample size. So let's play around a little bit. Let's see what happens here. What you'll see here is I have a population distribution, which is this solid black line, and I have a dashed line that is the sampling distribution. Now, in this case, the population distribution is normal. And that's not always the case, but remember we said that as long as our situation meets certain assumptions and conditions, we know that our sampling distribution, while the population might not, the sampling distribution should approximate normal. You should also see that there's something different between these two. The sampling distribution here versus the population distribution do not have the same height, which is frequency, or width, which is spread. And that's because in a sampling distribution, the square root of the sample size itself is used in determining the standard deviation. So this has a sample size of 5, so that means the standard deviation between the black line and the dotted red line is divided by the square root of 5. If I were to just adjust my sample size, let's take it to 25, you can now see it looks to be that the population distribution has decreased, but in fact it hasn't. In order for us to see the top of the population distribution, the scale has been adjusted. Now, the sampling size went from the square root of 5 in the denominator for sampling distribution to the square root of 25. You can see that that made my spread narrower. If I increase that to 50, it's narrower still. The maximum this slider will allow me to go is 250, and you can see the difference between the sampling distribution and the population distribution. Okay, so I'm going to drop that back down. Let's just start thinking about a sample of size 5. Now, if I change my confidence interval, notice how it does not change the graph itself. The confidence interval does not deal with adjusting either the population or the sampling distribution. Let's see what happens if I take a sample of size 5 and create a confidence interval off of it. Here you can see my sample, and the sample is distributed more centered to where the population is centered, but we have the chance for an outlier. The average of all of these samples is this big black dot, and the confidence interval created using the 95% confidence level, you can see expressed by the black line. Now, if I increase my confidence level, and I am more certain that I'm going to capture the true population parameter, the green line, my black line extends. If I decrease my confidence level, then that means my window itself shrinks. So that means the window that I'm talking about, my window of interest here, is much narrower, but what will happen is I increase my samples, there's going to be a higher chance that one of these samples just does not actually capture the true population parameter. Now I've done 10. Each of these 10 have 5 samples within. Those 5 samples are capturing or calculating the mean of them and the resulting confidence interval. If I were to tack on an additional 25, the original 10 are still here, but what's happened is just by random sampling variability, I have some samples that have their averages well outside of the range of the others. And because of them, my 80% confidence level does not allow for a confidence interval that captures the true population mean. Now, if I do another 25 and another 25, you can see what happens. At an 80% confidence level and 85 total samples taken, 68% of them should result in capturing the true population parameter. If I widen my confidence level to, let's say, 90, it's not exact that 90% of my confidence intervals created will capture it, but you see it becomes more approximately appropriate. Now, if I increase it to 95, you can see the comparison against the confidence level and the percentage of my confidence intervals that truly capture the true population mean. Now I'm going to reset this and I'm going to change my sample size. Remember, we said that we like to have a sample size of at least 30 in order to really talk about a sampling distribution that should approximate normal. And rather than showing you each individual sample, here's 25 samples, another 25, and another 25, and yet one more. Now, unfortunately, just because of the size of these, I don't believe I can get it so that nothing I do to the size here is going to allow us to see all of those sampling distributions at the same time. You can see the most recent ones. But what you can see from here is out of all of that, at a 95% confidence level, a sample size of 30 allows me to catch 93% of the time the true confidence interval. If I change that to 99.5, that's almost 100%. Look at this. And that means out of the 100 confidence intervals I've created, 99 of them did in fact capture this green line here. Now, I can't just change that line because each of those samples, you see when I changed this number, those points dropped away because those confidence intervals were only based upon the given data that I had. So if instead now I take a sample of 100, you can see the distribution here. You're most tightly clustered where a majority of your population lies, but you have a couple as the population spreads out further. You can take another one and you can see that these tend to be very, very similar. And I'm going to drop this confidence level down to the standard 95%. And what we can see here as I go through this, for each sample is completely different. We grab from different points. And sometimes these samples are going to capture the true population parameter, the green line, but sometimes it doesn't. So now I've done 20 samples. And out of those 20, I've had one that did not capture it at all. Some of them came close to not capturing it. Some of them were almost perfect. And that's because of your natural sampling variability. Let's just do 5 more this way. This is really nice because it shows you that not only is your data going to come from the center of its distribution of the population, but you do have some outliers. And those outliers affect your spread. Now, if I do another 25, another, and another, you can see I've now completed a total of 100 samples of size 100. And out of those 100 samples, 96 of them captured the true population parameter. But if I narrow the parameter, another common number used is 90%. You see it's all the same starting spot. I'm not changing the average of any of those samples, but what I am changing is the width of my interval. The more the less confident I am, the narrower my interval gets, but that also means that I capture less of the data. If I want a really good confidence level, I have a much wider interval, but I have a better hit. So we're trying to make a balance between those. So what we're trying to do here again is to find a balance between certainty and precision. Remember, certainty is the amount of faith that you have in your estimation, in your sample, and that's your confidence level. Your certainty, if you are 100% certain, that typically results in a very broad confidence interval. Whereas if you want to be precise, you want to be specific and to the point. A 95% confidence interval states that you believe that your observed statistic, your p-hat, if you were to stretch out two standard errors, remember that's your standard deviation, calculated based off of your actual estimation of your sample statistic, you would then believe that 95% out of 100 times you would contain the true population proportion. Where that plus or minus 2 SE of p-hat, that is your margin of error. And your margin of error itself, its size, is dependent upon what your standard error is. And again, in general, our confidence intervals do have the form of your estimate of your sample statistic plus or minus whatever your margin of error is. And we adjust the margin of error by adjusting our sample size and our confidence level. The more confident you want to be, the larger your margin of error needs to be, making your interval wider. Now, when we talk about critical values, this is where our actual confidence level comes into play. The 2 in this formula, right here, that 2 deals with how wide you want your confidence interval to come from. And it stems from your 68, 95, 99.7 rule. So the 2 is using that 95. 2 standard deviations should capture 95%. The problem is that 2 is really, it's an estimation. And we can use either the table of z-scores, or technology, to find exactly what corresponds with a 95% confidence interval. And that's the z-score that corresponds with an interval centered about 50 that is 95% wide. And the z-score that compares with that is 1.96. It's close to 2, but it does result in a completely different calculation. That 1.96 is now called our critical value, and you'll see us talking about it in lessons and in formulas with Z star. Okay, so if you remember, when we have a probability that we're given, or a percent, because they're pretty much the same thing, if we want to find the corresponding z-score, the calculator command for that is inverse norm. And for your confidence level, you find the corresponding critical value, and that critical value tells you how many standard errors your confidence interval is going to go out. So those critical values, this is how it's calculated. A 90% confidence interval has a critical value of 1.645. And if you think about it, the empirical rule said 68, 95, 99.7. So I couldn't even use that if I wanted to create a 90% confidence interval. Well, how do we come up with these numbers? You take the fact that you have your normal curve. Your normal curve is centered on 0, which is 50%. And you want 90% to be balanced there. That means 45% goes out to this side, 45% goes out to this side. So if you take that 50 plus 45, the number that corresponds to this is a 95%. And the z-score that goes with 95% is 1.645. 50 minus 45% is 5%. So the z-score that corresponds with 5% is negative 1.645. There's your plus and minus. So, to find whatever your confidence level is, so if we want a 95% confidence level, we would say a 0.95 times 100 confidence interval. The formula that we use is this. inverse norm times 0.5 plus, you could do minus, it just gives you the negative, whatever your confidence level that you want. For example, a 95% confidence level, I put 0.95 over 2. If I want a 68% confidence interval, I put 0.68 over 2. And simply typing inverse norm 0.5 plus whatever your confidence level is as a decimal divided by 2, mean of 0, standard deviation of 1, will give you your critical value. I highly suggest that you write this formula down, as it will come into play in a majority of your problems, really, from here to the end of the school year. This formula right now, we're focusing on z-scores, but the same concept holds true when we start talking about other test statistics. So hopefully from this little video, you've realized that there is a link between a confidence interval, the sample size, and the confidence level. And the confidence level and sample size are the only things that we have control over changing. And the direct effect of changing the confidence interval, the confidence level, is found by changing whatever your percent is and calculating the corresponding critical value using inverse norm. All right, ladies and gentlemen, I will see you in class, and hopefully this gives us a nice starting point to actually sit in class and calculate some of these confidence intervals. All right, you all have a wonderful day.